Okay, we're going to analyze this circuit by applying the Thevenin-Norton equivalent. At the end, what we want is a Thevenin equivalent looking at the left of the interface. So we'll start off here with a 15 volt supply and a 3 kilo ohm. We're going to replace this with a Norton equivalent. So in that case, this would be our IN Norton equivalent of 15 volts divided by 3K, which in this case is 5 milliamps. Okay, and the Norton equivalent, looking at the terminals between A and B, would be $3K here. But we note that this 3K is in parallel with the 6K, and we can add up the currents that are in opposite direction with the 2 milliamp, between the 2 milliamp and the 5 milliamp current source. So taking this, we have a Norton equivalent. We're going to replace it, so this would be C and this would be D. This is the 6K, and what we have is a Norton equivalent of 5 minus 2 is 3 milliamps. We have a parallel combination, so that's basically an R equivalent of 3K times 6K over 3K plus 6K, and that turns out to be 2K. So we have a 3 milliamp current source in parallel with a 2K resistor looking to the left of terminals C and D. We can replace this with a voltage or Thevenin equivalent. So that is now 3 times 2 is 6 volts now, and we have it in series with the 2K. Now let me find some room here. So in this case, this is again between terminals C and D. So we see it's, when we convert that, this 2K is in series with this 3K as well as this 4K. So when we rewrite this, so taking this 6 volts and 2K, that's now in series with the 3K and then the 4K at the bottom. Now when we simplify this, doing the open circuit voltage VOC with the open circuit load, which implies R is infinity, so no current flow is going through here, we have 6 volts. When we place a short across here, we have 2K, 3K, and 4K in series, and that's the same current going through these 3 devices when we have a shorted load, where R is infinity. So the current, basically, our short circuit current, is equal to VOC divided by the sum of the resistance here. 2K plus 3 is 5 plus 4 is 9K, or 6 volts divided by 9K is 2/3 milliamps. So now that we have 2/3 milliamps as our short circuit, we can calculate our resistor, and it's basically again 2 plus 3 is 5, 9K. So one way to find the equivalent resistance is to get rid of all the independent sources, looking here, short it out, and we can just add up the resistance. So our RT in this case is 9K. So now we can take everything to the right of this interface here and convert that into a 6-volt source, a single 6-volt source, and a single 9K resistor to the left of this arrow. And then we'll connect it to the load. So let me simplify that circuit now, where we have of a 6-volt source is our Thevenin voltage and our Thevenin resistance. So we'll call that VT now. RT is 9K, and we just connect that to a load. Now let's try some different loads, circuits. So let's just say it just consists of a simple 10K resistor. So let's say RL is 10K, and we want to find that the power delivered to this load. And then we'll try another load where it's a load of consisting of a voltage source of 5 volts as a voltage source, and L is a load, so that's 5 volts. And we want to find the power associated with that device. So here we have RL is equal to 10K. So that means we have a current going through this load, call it IL1, is equal to 6 volts divided by the total resistance here, 9K plus the 10K load, which is 19K, which is equal to 0.3158 milliamps. And the power dissipated is just I squared R. So the power is that we square the current, 0.3158 squared times 10K, and that yields 0.9973 milliwatts. For the 5-volt source now, we'll change the load, and notice we didn't change the source circuit. See how it simplifies our analysis when we change the load? So here we have a 5-volt load, so the voltage and current going through the 9K resistor is, the voltage difference is 1 volt. 6 minus 5 is 1. So our current going through here is just simply 1 volt divided by the 9K. And with that, we have the current, we'll call it IL2, 6 minus 5 divided by 9K is equal to 0.111 milliamp, and the power to the load, delivered to the load, is simply power times IV. So here 0.111 milliamp times 5 volt is simply 0.555 milliwatts. In this case, the voltage source load is absorbing rather than delivering power. And a typical example of this situation is a battery charger. Just a comment that the Thevenin equivalent allows us to calculate the power delivered to the load, but it does not tell what power is dissipated in the source circuit. In other words, the Thevenin equivalent circuit has the same IV characteristics at the interface, but it does not duplicate the internal characteristics of the source circuit.